Machine learning is transforming building energy control, but most data-driven models fail the moment they encounter out-of-distribution conditions. Why? Because training data from standard HVAC controllers only captures narrow, stationary operating bands. When deployed under new weather patterns or occupancy profiles, these models extrapolate poorly, often collapsing back to the mean of their training distribution. The solution is deliberate state space excitation, actively stimulating control inputs to force the building through diverse thermal states. BuilDyn solves this by extending the BuilDyn framework. It wraps functional mockup units through the FMPy API, giving you a clean Python interface to inject custom control signals, sample from representative building parameter distributions, and chain-dependent parameter conversions directly into your ML pipelines. Here's how the excitation layer actually works. BuilDyn implements 3 complementary strategies. First, Poisson excitation. You sample heating signals from a Poisson distribution, generating irregular, piecewise constant step inputs that break stationary assumptions and probe low-frequency thermal inertia. Second, sinusoidal excitation. It chains sine waves with randomly sampled frequencies and amplitudes, separated by steady-state holds to mimic realistic periodic load variations and capture envelope dynamics. Third, and most effective for control-oriented modeling, is ramp excitation. It linearly ramps heating between minimum and maximum bounds, with deliberate holds at the extrema. This systematically probes transitional dynamics, forcing the model to learn how thermal mass responds to continuous rate changes rather than just equilibrium states. The performance gap is stark. We train transformer-based prediction models on data from a standard Pi controller versus BuilDyn's ramp excitation. The excited model achieved a 96% action-response correctness score, compared to 76% for the Pi-trained model, and only 54% for a generalized transfer learning baseline. ARC measures whether the model correctly predicts the physical direction of temperature change, given a control action. Excited data doesn't just lower absolute error. It eliminates the tendency to revert to training distribution means, yielding models that actually respect building physics under unseen conditions. This is foundational for scalable control-oriented modeling and building specific foundation models. If you're working on data-driven HVAC control, transfer learning, or gray box identification, BuilDyn gives you the state space coverage you've been missing. The paper and open-source repository are linked in the description. Tell me in the comments which excitation strategy you'd validate first on your own datasets.